All right, so hi all, I'm Julian. I'm an assistant professor at UT Austin. I've been there for about a year. I think actually almost exactly a year because it's the first week of classes right now, so don't tell my students. So yeah, I'm going to tell you about, what we've been talking about today, clustering of galaxies, reionization. And I want to, on the last talk of the conference, so I want to start with the same graphic we had in the very first talk. So thank you, Caitlin, for sharing this. This is a plot of star formation rate density as a function of redshift. You can see measurements pre-JWST, how over time this quantity went down. There's less star formation at earlier times. That's because there's less halos that host fewer galaxies. And as Peter is telling us today, the one thing we're pretty sure about in galaxy formation is that they form on dark matter halos. That's the one thing that seems to be consistent. Now, of course, once we turned JWST, what we started to see was a deviation from these sort of extrapolations based on halo mass functions. So we started to see higher star formation rate densities. Now, the dust hasn't quite settled on this, but pun intended, but it seems to be more star formation. And this is something perhaps we should have expected, that these extrapolations we're used to would break down. When you go to high redshifts, timescales are shorter, densities are higher, different feedback processes, dust might be different metallicity. So the question is the galaxy halo connection broken? And when I say broken, I mean specifically, is it different from what we're used to at low redshifts? So I'm going to give you a graphic that kind of illustrates what we've been talking about today a lot in terms of clustering. So if you have a very tight halo-galaxy connection with no stochasticity, scatter, burstiness, whatever you want to call it, what you have is big dark matter halos, so say big circles, are the brightest objects, the darkest, and then one-to-one you can connect a halo to the galaxy that lives in it. If you break this, you add a stochasticity, what you start having is sometimes the bright galaxies live in very small mass halos. And the very big halos sometimes are very faint. There is something that has observable consequences. So it will impact the luminosity functions. So if you go to the redshift 11 luminosity function, this is from Sears data, and you can look at more up-to-date observations, but they roughly stay around the same. All these pre-JWST models of redshift 11 fall short. There's not enough galaxies. If you have burstiness, suddenly you can fit it. And when I say burstiness, I mean it's one free parameter, just like how wide do you make this connection, how much do you break the halo-galaxy connection. And the way you're fixing this is essentially you're getting small mass halos that will live all the way on the right of this plot, and you're actually making them bright. Because there's so many of them, you actually can fit the data. Now, of course, this is not the only solution. You can just make galaxies more efficient on average. Either start forming stars, are emitting UV, you get rid of the dust, whatever you prefer. These are two different ways you can fit the data and the luminosity functions. And you can think of them as families of solutions, right? Burstiness doesn't have to imply star formation history burstiness. It could be variation object to object. Same thing with the blue line is like all objects are brighter on average. So you can ask, how do you distinguish this? Well, I'm going to take a little detour and take you to redshift 4, a very boring low redshift 4 that we've heard about. This is not a new problem. You can luminosity function. You can take one of these halo-based models. You fit a bunch of parameters, and I'm going to vary between these parameters. I'm going to show you two of them. You can add the amount of burstiness versus star formation efficiency. And all of these are within the 2 sigma, all these lines, and they fit relatively well, comparably well, but they have very different galaxy formation properties. You can be very bursty and not very efficient, or vice versa. And you kind of know what the panel is going to be on the bottom because Peter gave it away in his talk. It's the bias. The way you break this degeneracy, or one of the better ways to break this degeneracy, is by looking at the clustering of these objects. When you're very bursty, so you're on the red points, you actually have low biases, because small mass halos are the ones that are bright, are the ones that are occupying the bright and the luminosity function. Whereas, if you don't have a stochasticity, you're in the blue side, you have to be in very, very heavy halos. Now, these data points here are from Subaru. They should be taken with care because they haven't been reanalyzed, and we heard about today about what this looks like for AGN as well. But going back to cosmic dawn, first billion years, JWST, you can try to fit the luminosity function and then say, what has happened to the clustering? Well, if you think in terms of these plots, this cute graph I've shown you before, if the brightest galaxies are not in the biggest halos, the bias will be lower. You can predict what this looks like in current data, and Peter already showed this plot. When you have stochasticity, you have lower biases on average. And not only are they lower, but they're actually distinguishably lower by current JWST surveys that are ongoing. So the reason I highlighted Cosmos Web there was because it's a large area and it's contiguous. And that's the kind of thing you need to do to measure a bias, to measure the 2-point function on large scales. Otherwise, you get into this one halo term where there's a lot of information that is harder to extract. I wanted to highlight this data point from Dalmaso, which actually came up in Mark's talk before. This is a measurement, tentative measurement about bias plot 10. It's very, very large bias. And at face value, it seems to be preferring no stochasticity, the blue curve. Now, I would say, do not overinterpret this point yet, because this comes from a very small selection of objects, photometric, and in addition, doesn't have this large-scale 2-halo term clearly defined. So it's hard to say, really, you're seeing the bias or you're just seeing a 1-halo term clustering. But that's what I wanted to say about clustering, and I want to zoom out even more from galaxies to dark matter halos to the IGM overall, and talk about reionization, the other half of today. I want to tell you what all these JWST galaxies are telling us about reionization now. I want to take a historical approach. So I'm actually going to start about the year 2000. I'm going to tell you what we have learned about reionization, and many of you actually figured this out, so interrupt me if I'm wrong. So circa 2000, we didn't know that much. The CMB was boomerang. There wasn't a really good understanding of when reionization happened. And as we heard earlier today from Valentina, the first reionization era quasar spectra were about 2000, 2001. That's when Gamp-Pearson trough was detected. When WMAP turned on and we started having Lyman alpha forest data, we kind of knew that it had to end at about redshift 5. We didn't know when it begun. First WMAP data suggested the halfway point of reionization is like redshift 15, crazy high. People had 17. Yeah, people had to cook up models. There were not enough galaxies to get that high. Top 3 stars, dark matter annihilation, everything was game. Over time, it came down. Not only did it come down, but we started to get surveys at higher redshift from Hubble. So you were able to probe earlier galaxies. Redshift maybe, reionization was 8, 9, 10. But still, there were not enough. We hadn't reached enough photons. But then in 2015, something happened. Planck turned on, and redshift reionization went down. Also, Lyman alpha forest was getting even better, so we knew that reionization had to be over redshift 5, 6-ish, and midpoint was like 8-ish. And we had even higher redshift data from Hubble at this point. So for the first time, people were able to sit down, do the math, and say, hey, we've reached the galaxies that should be driving reionization more or less. And different teams did this, and I'm going to highlight, so Brand and Richard both at the same time wrote papers saying, hey, you do the accounting, you assume reasonable things for the emissivity of galaxies, escape fractions, you can get reionization to work out. Rents about redshift 6. Galaxies can do it. Piero at the same time wrote a paper about AGN, so you can choose which flavor of reionization you want. And they give you something that agrees with the CMB, so the optical depth on top is within the measurement. Lyman alpha forest, as Martin told us today, tell you when it ends, so all this part agreed as well. So life is good. We saw reionization, right? And now what I tell you is what is JWST telling us about this, and some of the properties that were assumed we can better directly measure now. So one of them, and I'm going to show a very controversial slide, is the ionizing efficiency. So this is a compilation of different measurements in the first couple of years of JWST. The y-axis is how many UV ionizing photons per star formation rate versus UV magnitude. The pre-JWST typical value folks would assume is this black line. And these are a collection of different measurements. The Tony Pauls in green and Hakim Attacks in gray are spectroscopic. The rest are photometric. Some of them are relation derived from galaxies. Some of them are points. And what I would take from this is there's no clear consensus. Measurements are all over the place, but they all seem to be higher than we had before. Some of them are like redshift 4, 5, 6. Some of them, Simmons reached up to redshift 9-ish. They all seem to be higher. So when you put this together, and for example, you can take the one from Simmons here and put it into this relation we had before, suddenly reionization ends earlier than we would like it to be. So particularly redshift 8 or so. And the optical depth is too high. So that's not good. So you can say, well, there's another ingredient we have to assume, escape fractions. This is, maybe the hardest one to measure. You cannot measure their reionization. What folks have done over the last years is go on low redshift galaxies, look at analogs, and try to study what this escape correlates with broadly. What galaxy properties can I look at? So 2 years ago, John Chisholm at UT, using the low redshift Lyman continuous survey, LCLCS, was able to find this correlation between Lyman continuous escape and UV slopes. So bluer galaxies towards the left have higher F escape. A lot of it may have to do with dust. redder galaxies are dustier, so then they also absorb more ionizing photons. And if you look at what we've learned from JWST over the last couple of years, and we heard about it this week, is early galaxies seem to be bluer. So you look at results from JADE, for example, or redshift 7-ish, you get UV slopes from around this regime. So at face value, this gives you large FSKs, maybe 10%. So if this relation holds up high redshift, and that's a huge if, you can go back, plot in this plot, and it's a lot of photons. So at face value, you take ionizing efficiencies, you take escape fractions extrapolated to high redshift, and this tells you reionization should be over at redshift 9, which it isn't. We know. Both from the CMB and from the Lyman alpha forest, and Chris told us today in his talk how the Lyman alpha forest doesn't allow this. So we're in a pickle. We have all these photons, we have all these galaxies, and reionization should end earlier than it is. So what's wrong? What's going wrong? So the first thing you may assume is maybe there's some subtle thing, something like these ionizing efficiencies I was telling you about. So there's different disagreement between groups. For example, the Simmons group put some particular cut on which galaxies they selected. Ensley didn't, but it was photometry. Paul was a spectroscopy, but has a selection function because it's spectroscopy. So if you just take 25.5, which looking at a few slides ago is roughly like, towards the lower part of where these measurements are, you still have a problem. If you increase the number of recombinations, and there's theoretical reasons to do so, for example, Fred Davis has been arguing for years there's more recombinations than we expected, and recently claims to have measured a higher recombination rate on the Lyman alpha forest. You can also move this curve, but you don't move it enough. You don't get all the way to where we should be. Of course, there could be more than one of these solutions. There could be selection functions. There could be more recombinations. But you could also think, let's bring the big guns. Let's bring the big guns. How do I actually change this dramatically? And you have to essentially give up one of the measurements. You can either give up the ionizing efficiency, so you cut the luminosity function, the ionizing production. So something where you say, below, say, -17 magnitude, I don't emit ionizing photons that escape. Something that will look like oligarchic reionization. Or you say, well, the other way, I'm going to say that F escape is wrong at high redshift. There's different mechanisms setting it. I cannot know anything about it. So I'm just going to set it to below, say 3%, which is about a factor of 5 less than you expect from these analog studies. And that will look more like democratic reionization. It's slower and, smooth. And the last point I want to make about this is something that looks, in principle, looking at the neutral fraction, you can actually learn. But you can actually always tweak these parameters. So the message I want to leave you with is you can always cook up models of reionization that are either democratic or oligarchic that have roughly the same neutral fraction versus redshift. But they're still different. They have different bubble radii, different clustering properties. This is something you hope to measure through Lyman alpha studies, 21 centimeter. Unless you're Joe, then I guess you don't have hope for 21 centimeter. But I do. And there is hope to actually measure the properties of reionization through how the reionization studies cluster. So the final message of my talk is there's a lot of things in which you have the same average quantity and different clustering. In the top part, I've told you about galaxy formation, how we can distinguish burstiness by connecting the galaxies to dark matter halos, which we can do through clustering. In the bottom part, I've told you about reionization, how we can learn who's driving it, if it's galaxies, if it's AGN, if it's thin galaxies, brighter galaxies, by studying their clustering properties. And this is going to tell us, I would say, arguably, what is happening. Rather than looking at one-point functions, we look at two-point functions or beyond. Thanks.
Thank you very much, Julian. Let's see if there are questions. Rafa.
Thank you, Julian. So my question is, can't we also try to put these two things together? I mean, the fact that you have much burstier star formation, wouldn't this affect the way you measure Xion and the way you estimate that? I mean,
yeah. Yes, no, absolutely it would. And this is something that, as far as I know, is still like in flux. But you could imagine that as you go maybe towards the faint end, things are in an off mode, and then you actually they're not emitting in like short timescales, like tens of million years, and then the psi ion go down. So in some way, if you look at the Ensley measurements, those are not putting a cut in any like line emission or anything, and they seem to be going down. Now, if you something exercise you can do is you can actually join these 3 points through a line, which, dubious, but you can do that, and you still get, again, more photons than you expected. So the off mode will have to be more off than we have currently seen, but it could still be.
Thanks for such a nice talk. I just have to comment on one of the comments you made about selection functions and Xi-ion. So in Tony Paul's paper, where we estimated Xi-ion spectroscopically, we did a very close comparison with the Simmons et al. Sample and actually found that the Simmons sample is biased high in Xi-ion at a fixed MUV as you go fainter, and that's what induced the apparent anti-correlation with Xi-ion and UV luminosity. So I think, if anything, the spectroscopic sample that we analyzed was more complete. Even though it's true you have to detect a Balmer line, we found that there seemed to be some incompleteness in the photometric samples.
That's good to know.
Yeah, and also when we used the Xi-ion, and we appreciated all your help with this, that Tony found, we find that reionization completes at around redshift 6. So,
Joe.
Yeah, great talk. I like how you revisited this and made us all realize that things are maybe not as kosher as we thought they were. I just wanted to say that I do think that the Lyman alpha forest fluctuations that Shriyakar Martin talked about, and also Nick Nedden's been doing this in Hanjue. Ju also mentioned this in her talk. But I do think that can sort of break this degeneracy between oligarchic versus democratic types of reionization. The problem really is that everybody's just running one model, which kind of comes back to Benedetta's talk. But I think there's a lot of potential there until 21 centimeter maybe works or maybe doesn't.
Very soon works.
Yeah.
That's what you mean, right? Yeah, no, I think that's true. Like, we need better tools to analyze the beautiful data we have while we wait for other beautiful data. That you need things that are fast and efficient.
Great talk, Julian. Thank you so much. This doesn't include any AGN, right?
That's correct.
So if
thank you for
if
saying
AGN emit any ionizing photons, doesn't that make all of this even worse?
I put this and I forgot to say it. That's yes.
Yeah.
If Piero's right, we have twice as much
reionization. If Piero's right, then we're in deep something. Yeah.
That's right. And in fact, I would argue this is in that way. Yeah, I'm not ignoring all AGN. At the very least, there will be some at the least, if not all. So that's more trouble. Yes, that's a good point.
Well, if I'm
Yes. Why is now the universe reionized earlier? You tell me. You've been doing this longer than me.
Yeah, Martin.
No, I think maybe you should pay more attention to the way you're estimating F escape is not really seeing the photons. You have some measure where you think you sort of have accounted where the photons went, but these emission line ratios to turn these into an escape fraction is a very indirect method.
You mean a low redshift or a high redshift? At high redshift, you don't see it at all. But low redshift, you do see them.
Yeah, at low redshift you do them, but at high, we're talking about what you're doing at high redshift.
Right. So yeah, high redshift.
So I'm not convinced that I should believe any of these F escape numbers.
That's a fair comment. I'm not a low redshift F escape observer. There's a physical correlation they find that seems to hold from redshift 0 to 3. So the Vandal survey at redshift 3 actually finds the same correlation. It could break a higher redshift. There's reasons that it should break. But if this is the problem, I would say we need to understand why. Like, what is actually different?
I mean, just a small comment. I mean, we've looked at how F escape correlates with various galaxy properties. I'd say that UV slope is not the one that shows the tightest correlation with F escape, as opposed to things like Lyman alpha equivalent with H1 covering fraction. Those are very tricky to measure. But beta, I think, has a fair amount of scatter, which I know you're taking into account.
I would say, I think you can measure also at redshift 8 or 9 would be ideal. Yeah.
Harley.
Yeah, I just wanted to make the point that I think this is too simplistic with F escape, because, I mean, you can look in Michael Topping's papers, you can look in basically anyone's papers who's just taken a simple stellar population and asked what's the beta slope with 0 F escape. So, just a cloudy model, and you get a value around minus 2.5 at 0. So if you're assuming that, based on this correlation, it's 20% at minus 2.5, it could be anywhere between 20% and 0. So I think this is just wrong.
I'm not sure I follow the argument, but I'll say if you think there's a better way to do it.
No, there is.
Like,
in fact, we try to avoid this.
We cannot measure FSK by Redshift 6, full stop.
No, we try to avoid this, but all I'm saying is if you run a simple cloudy model where you make sure that you integrate it all the way to the ionization front, so no photons are leaking, okay, a simple burst, you can get a slope of actually bluer than minus 2.5, depending on your assumptions. And so to assume every galaxy that has a slope of minus 2.5, which is many of them at high redshift, has an escape fraction of 20%, just can't be right.
I mean, no, you assume a PDF. You assume that there's some distribution. But a distribution could be wrong. If your point is you should redo the distributions, I'm all for it. Like, this is the first thing you can do. And as I said, this is the hardest one to do.
Yeah, I'd like to make a final comment. I think that concerning the burstiness, I think we all agree that there is burstiness, and clustering is also a fantastic way to test it. On the other hand, we know already now that we can't allow for a degree of burstiness that is too large, because that would completely ruin or would be completely inconsistent with the mass metallicity relation that we are measuring on this redshift, because too much burstiness would spread around all the points, would create this chemical chaos or whatever it's called, right? And so I think that this is something that can be put together to the clustering measurement. So it's yet another method to constrain burstiness. And that goes back also to what Avishai and Mark were discussing before. So very final question, if there's one, short and quick. Okay.
Thank you for a nice talk. And so can I ask, so there is possibility that higher clamping factor, and so what can cause that?
What can cause it?
Yeah.
Oh, that's a question. I mean, I would argue that we don't actually understand that well in hydro simulations, and Nick actually wrote a paper on this very recently, Nick Nettin, like what is actually how large you expect it to be. It grows towards low redshift, and if you actually look historically what the values have been, as simulations got better, it has changed. So like taking 3, taking 5 is reasonable, but taking 20 maybe is not that unreasonable. And Fred Davies seems to be finding that on the Lyman alpha forest from the mean free path. So I don't have an answer.
Well, it used to be mini halos, right? That were producing the sinks, but still is. Okay. Good. So we're coming to an end. So let's take Julian again.
Thank you.
And